In our previous video we showed how to calculate and measure peak-to-peak voltages with a high bandwidth oscilloscope. And we found a problem. The agreement between simulations and measurements was not good when we worked at the highest frequency our oscilloscope should measure. Now we will investigate what was the reason. In the previous video we arrived to an expression that can predict the peak-to-peak voltage delivered by the generator to our oscilloscope. We used this expression and could successfully predict measurements at 50 MHz, which were made with oscilloscopes having bandwidths between 0.5 and 12 GHz. But when we tried to do the same at the maximum operating frequency of the oscilloscope, we obtained disappointing results. Let us investigate what was the reason. The first thing that comes to our mind is to check the output power of the network analyzer, which was used as a single power generator. Was the power exactly 10 dBm as we thought? With a little help of some friends, we could use a spectrum analyzer to accurately measure this output power. And these are the results. A network analyzer is an instrument designed to measure these parameters of a linear two-port network, and therefore it does not need an accurate calibration of the output power. Anyway, after improving the accuracy of our calculations with these new measured powers, we observed that clear discrepancies between simulations and measurements still remain. There is indeed another source of error that is more important. This is the front panel of one of our oscilloscopes. We find an auto-scale button that enables one to easily coach the signal, and of course one can also set the vertical scale. Well, let us use these controls and pay attention to the readings. The frequency will always be the maximum operating one for the oscilloscope, in this first case 12 GHz. We activate the channel and press auto scale. The signal is a bit noisy, but I can improve this with the averaging. I go to Setup, Acquisition, and enable averaging. Now I see around 300 millivolts, then I reduce the amplitude scale 600, reduce again and got 1.1 volt, 1.4 volt, 1.45. The Infinium doesn't allow me to go to lower scales. Now I check this with the Yokogawa. Activate the channel, auto setup. I press measure to display the measurements, and I go to acquisition, mode, and average. Now we go to maximum resolution and get around 800 millivolt. I start to reduce the scale and get 1.2 and 1.7. Again, I cannot go to lower scales. Finally, I check this with Tektronix. I press averaging and get 1.9. Now it's 2.0. Around 2.1 and 2.2. This table shows the measurements we did with the less accurate scales. Now the agreement between simulation and measurements is not bad at all. This might seem quite surprising. If you look around the web, you will find tons of videos and technical notes recommending you to use the highest resolution scales. The auto scale button of your oscilloscope will probably try to do so. Indeed, there is a good reason for this. All digital scopes have a limited amount of vertical resolution bits, could be 8 or 12 in enhanced modes. You want to take maximum benefit of them, but at the same time you might be paying a large price for this. You might lose accuracy due to nonlinearities or internal protection circuits of the oscilloscope. What about considering mismatches in the simulations? We might say that the agreement between simulation and measurement improves a bit in our Tektronix for this case, but no significant changes are seen at all. As we spot in our previous video, all oscilloscopes are very well matched to 50 ohm. It could even happen that some manufacturers already include internal corrections to fix the known mismatch effects, as it is done in the calibration of a power meter. In summary, we have navigated through some typical mistakes one might commit when measuring high-frequency voltages in time domain. First, you want to ensure that your generator provides the power you expect. A spectrum analyzer or a power meter can help you to check this. In addition, beware of the mismatches. It is difficult to find information on how they are internally accounted for by the oscilloscopes. If they do so, probably the oldest or cheapest instruments don't correct them. And in many cases we certainly don't need the large amount of digits we get at the most sensitive scales. Only the first 2, maybe 3 digits are repeatable. If you go for maximum resolution, it is certainly important to check for nonlinearities, especially if you are working at the highest operating frequency of your oscilloscope.